On the far side of the Moon, there is a crater 72 meters across. It has no name. It is too small to appear on most maps. But in May of 2019, a rover the size of a small desk rolled to its rim and pointed a spectrometer at a rock. The rock returned a reading that had been sought for decades: olivine and low-calcium pyroxene, minerals that do not belong to the Moon's crust. They belong to the mantle, the deep interior of a world, and they were sitting on the surface because something had torn the Moon open and scattered its insides across the ground. The largest impact scar in the solar system, a basin the width of a continent, carved by a collision that nearly shattered the Moon, had finally given up its secret, and a small, patient robot from China was the first to see it. Hello, and welcome to Sidereal. This is the story of the Chang'e 4 mission, the far side of the Moon, and what we found when we finally looked at the one face we had never seen. If this is your first time here, please subscribe and like this video. In the comments, tell me where you are in the world and the local time. I read them before the next video goes up. 4 questions will carry us through tonight. What kind of collision is large enough to nearly break a world in two? And how do you find the scar it left behind? Why did the deepest hole in the solar system hide the one thing it should have been full of, for decades, from every instrument that looked down at it from orbit? What does a rover do, alone on the far side of the Moon, when no signal from Earth can reach it directly? And what does the silence up there, a silence deeper than anything that exists on our own planet, have to do with the very beginning of the universe? In 1959, the Soviet spacecraft Luna 3 took the first photograph of the lunar far side. The image was grainy, transmitted across 380,000 kilometers of space, and it revealed something unexpected. The near side, the face we see from Earth, is dominated by the dark plains called Maria, ancient basalt floods that filled giant impact basins. The far side was different. It was almost entirely bright, heavily cratered highlands, with only a few small dark patches. The asymmetry was stark, and no one could explain it at the time. Better images followed slowly, and from an unexpected direction. The Soviet probes Zond 3 and Zond 6, launched in 1965 and 1968, returned higher resolution photography of the far side as part of the broader, ultimately abandoned Soviet effort to send cosmonauts around the Moon ahead of the Americans. And in December of 1968, the crew of Apollo 8 Frank Borman, Jim Lovell, and Bill Anders became the first humans to see the far side with their own eyes, sweeping past it during 10 orbits before returning home. For the brief period each orbit when their spacecraft passed behind the Moon, every radio link to Earth went dead, the same fundamental fact of geometry that would later force Chang'e 4 to rely on a relay satellite rather than a direct signal. The crew described the far side afterward as more heavily cratered and rougher looking than the familiar near side, a battered, almost forbidding landscape with none of the smooth, dark plains visible from home. They were close enough to look directly at terrain no human had ever laid eyes on, too far away and moving too quickly to land on any of it. Every Apollo mission that followed photographed more of the far side in passing, on its way to and from a near-side landing site, building up a patchwork of imagery good enough to notice that one circular shadow near the South Pole was unusually large, but not good enough to say anything more specific than that. For the next several decades, the far side remained something the United States and the Soviet Union had only ever flown past. Nobody had any plan to actually go there. There was, for most of that time, very little reason to. The near side had everything anyone needed for a crewed landing, direct line of sight to Earth, straightforward communications, a known safe environment. The far side offered scientific curiosity and nothing else, and curiosity alone rarely funds a spacecraft. What the photograph also revealed, barely visible in the shadowed southern latitudes, was a very large, very dark circular feature. It would take decades of orbital mapping to confirm what it was. Clementine, a joint NASA and Department of Defense mission launched in 1994, mapped the Moon's topography with a laser altimeter and confirmed that this feature was the deepest, largest depression on the entire lunar surface. Lunar Prospector, launched 4 years later, measured its gravity signature and found the crust beneath it was anomalously thin. The basin had a name now, the South Pole-Aitken Basin, after the two features that mark its rough boundaries, the lunar South Pole, and the crater Aitken, itself named for the American astronomer Robert Grant Aitken. From here on, we will mostly just call it the basin. There is only one this large, so there is rarely any confusion about which one is meant. The numbers are difficult to hold in the mind. The basin is about 2,500 kilometers across. If you stood at its center, the rim would be over the horizon. You would not know you were inside a crater at all. You would be standing in a bowl so vast that it spans roughly the distance from New York City to Denver. Its floor sits 13 kilometers below the surrounding highlands. The Mariana Trench, the deepest point in Earth's oceans, is about 11 kilometers deep. The Moon, a body 1/4 the diameter of Earth, carries a wound deeper than our planet's deepest ocean trench. You are standing, for a moment, at the center of that bowl. There is no rim in any direction. The horizon simply curves away, the same dull grey in every direction, broken only by smaller, ordinary craters layered on top of something far too large to read as a crater at all. On Earth, a hole this size would not look like a hole. It would look like the world itself had a different shape here than it did everywhere else. That is the closest most people ever come to standing inside the largest known impact structure in the solar system, and even this, a description built from careful orbital measurement, undersells what 13 kilometers of depth and 2,500 kilometers of width actually mean when there is nothing human-built anywhere nearby to give them scale. The impact that created this basin occurred between 4.2 and 4.3 billion years ago. The age is not precisely pinned. We will return to that uncertainty later, but the era places it squarely in the Hadean, the earliest and most violent chapter of the inner solar system's history. The object that struck the Moon was at least 200 kilometers across. For comparison, the asteroid that ended the Cretaceous period on Earth, the one that created the Chicxulub crater and wiped out the non-avian dinosaurs, was about 10 to 15 kilometers in diameter. The impactor that carved this basin was not a mountain falling from the sky. It was a small world. The energy released in that collision is estimated at roughly 10 to the power of 26 joules. That is a number beyond intuition. But here is one way to approach it. The largest nuclear weapon ever detonated on Earth, the Soviet Tsar bomber, released about 2.1 times 10 to the power of 17 joules. This impact released approximately 500 million times more energy than that. It melted thousands of cubic kilometers of rock in seconds. It sent shockwaves through the entire body of the Moon. It excavated a hole so deep that, according to every model, it should have punched straight through the crust and into the mantle beneath. The lunar crust varies in thickness. On the near side, it averages about 30 kilometers. On the far side, it is thicker, about 40 kilometers on average. Beneath this basin, in places, it is less than 10 kilometers thick. Some estimates place it closer to 5. The mantle, the layer of dense, slowly flowing rock that makes up most of a planet's interior, should have been laid bare. And yet, for decades, no one could find it. Orbital spectroscopy is the technique of identifying minerals from reflected sunlight. Different minerals absorb light at specific wavelengths, creating characteristic patterns that a spectrometer can read from orbit. Clementine carried a spectrometer. So did Chandrayaan-1, India's first lunar mission, launched in 2008. So did the Lunar Reconnaissance Orbiter and Japan's Kaguya Orbiter. All of them mapped the basin's surface composition. All of them found the same thing. The basin floor was dominated by anorthosite, a light-colored rock rich in the mineral plagioclase feldspar. Anorthosite is the primary component of the lunar crust. The mantle should be made of something else: olivine and pyroxene, minerals rich in iron and magnesium, much denser and darker than crustal rocks. The reason the crust and mantle settled into such different materials in the first place goes back to the Moon's very earliest history, when it was young enough to be substantially molten all the way through an ocean of liquid rock, covering the entire body, deep enough that the term magma ocean is not an exaggeration. As that ocean slowly cooled, different minerals crystallized out of it at different temperatures, and crucially, at different densities. Plagioclase feldspar, the principal ingredient of anorthosite, is relatively light. As it crystallized, it floated upward through the surrounding liquid rock, the same basic way a less dense object floats to the surface of a denser fluid and accumulated as a solid crust skimmed across the top of the cooling ocean. Olivine and pyroxene are considerably denser. As they crystallized, they sank, settling out below the forming crust to become the mantle. The result, after the magma ocean finished cooling, was a moon cleanly sorted by density, a light crust riding on top of a heavier interior. The lightest material on the outside and the heaviest pulled down toward the center, the way oil settles above water given enough time and no reason to mix. This is why finding olivine and pyroxene sitting exposed on the surface is so diagnostic. Under ordinary circumstances, that material has no business being anywhere except underneath tens of kilometers of the very crust it sank beneath, billions of years before anything resembling a rover existed to go looking for it. The orbital data showed almost none of these mantle minerals anywhere in the basin. This became known as the missing mantle problem. It was one of the quiet, persistent puzzles of planetary science, a basin deep enough to expose the moon's interior, and yet no direct evidence that the interior was there. The leading hypothesis was burial. After the impact, the basin floor was a sea of molten rock. As it cooled, it solidified into a dark, dense basalt, similar to the Maria on the near side. This basalt may have covered the exposed mantle, sealing it beneath a layer of volcanic rock. Later impacts, small and large, pounded the surface, churning the upper layers into a fine, powdery regolith, the crushed rock and dust that blankets the entire moon. If the mantle was there, it was hidden under kilometers of later deposits, invisible to any spectrometer looking down from orbit. To test this hypothesis, you would need to land on the basin floor and drive up to a fresh crater, one small enough and young enough that its impact had punched through the overlying basalt and regolith, excavating the material beneath. You would need to put a spectrometer directly on that exposed rock and take a reading. You would need to be on the far side, where no spacecraft had ever landed, and you would need a relay satellite to communicate through the moon's bulk, because the far side never faces Earth. That single requirement is most of the reason it took until 2019 for anyone to actually try. A relay satellite sitting usefully between the Earth and the far side is not, in itself, a difficult thing to build. It is a difficult thing to justify funding on its own, attached to no particular mission. For a destination nobody yet had a specific scientific reason urgent enough to act on. The near side, throughout the entire span between the last Apollo mission and the start of China's lunar program, kept offering more accessible, cheaper, equally interesting targets. Newer instruments returned samples. Polar ice once, that became the priority. The far side waited not because it was technically impossible to reach, but because reaching it required committing to extra engineering, extra cost, and extra risk for a destination whose specific value was, for a long time, mostly theoretical. It took a space agency with both the resources and the institutional patience to build a single-purpose relay satellite years ahead of the mission it was meant to support, simply on the expectation that the value of finally answering the missing mantle question would be worth the wait. Before we follow anyone to the basin floor, it is worth asking why the mantle mattered enough to justify the trip. The answer goes back further than this impact, back to the formation of the moon itself, and to an argument that took the better part of a decade to settle. In 1975, two American planetary scientists, William Hartmann and Donald Davis, published a short paper in the journal Icarus. Their proposal was that the moon had not formed gently alongside the Earth out of leftover material orbiting the young sun. It had formed violently, the product of a single, glancing collision between the proto-Earth and a body roughly the size of Mars. The debris from that collision, they argued, would have spread into a disk around the young Earth, and from that disk, the moon would have slowly gathered itself. The hypothetical impactor would later be given a name, Theia, after the Greek titan said to be the mother of the moon goddess Selene. The following year, the astrophysicists Alastair Cameron and William Ward proposed something very similar, largely independently. Neither paper attracted much attention at first. There were other theories on the table, and each one carried a specific, well-known flaw that none of their advocates had managed to fix. The capture theory proposed that the moon had formed elsewhere entirely and been pulled into Earth orbit later, intact, by gravity alone, but capturing a body that size, without either destroying it or sending it straight back out into space, requires an extremely narrow and implausible set of starting speeds and angles. the kind of coincidence orbital mechanics rarely hands out for free. The fission theory proposed that a young, rapidly spinning Earth had simply flung off part of itself, the way a fast-spinning ball of dough might shed a smaller piece. But no one could find a physically realistic spin rate that would actually do this without tearing the planet apart entirely in the process. The co-accretion theory, sometimes called the sister theory, proposed that the Earth and Moon had simply formed together, side by side, out of the same patch of the solar nebula, clean and simple, except that it offered no explanation at all for why the Moon's core is so much smaller, proportionally, than Earth's, when both bodies supposedly condensed from identical starting material. Each theory solved part of the puzzle and broke on a different piece of it. For most of the following decade, none of these ideas, including the still new giant impact proposal, had a clear advantage over the others. What changed the field's mind was not a new discovery. It was a deadline. In the early 1980s, 3 lunar scientists, Hartmann himself, along with Roger Phillips and Jeffrey Taylor, issued a challenge to their colleagues ahead of a conference scheduled for October of 1984 in Kona, Hawaii. They gave the field 18 months. Go back to the Apollo data. Go back to the models. Decide what you actually think happened, because showing up at the conference without a position was no longer going to be an option. It is an unusual way for a scientific consensus to form not through a single decisive measurement, but through an ultimatum that forced researchers to stop sitting on the fence. At Kona, the giant impact hypothesis emerged as the clear favorite. The other theories did not disappear entirely, but from that point on, there were essentially 2 camps left: people who accepted that the Moon was the debris of a planetary collision, and a shrinking number who remained unconvinced. The hypothesis has held up well in the decades since, though not without complications. It explains why the Moon has such a small iron core relative to its size. A glancing impact would have stripped away mostly rock and comparatively little of either body's metallic core. It explains the unusually high angular momentum of the Earth-Moon system, and it explains why lunar rock, brought back by the Apollo missions, turned out to be so geochemically similar to Earth's mantle, rather than resembling some entirely separate world. That last point has also been the hypothesis's most stubborn problem. If the Moon is mostly built from Theia, and Theia was a different body entirely, the isotopic match between Earth and Moon should not be nearly this close. One of the more striking attempts to fix this came in 2018 from the planetary scientist Sarah Stewart, then at the University of California, Davis, working with her former student Simon Locke. Rather than imagine the impact as a clean collision that simply flings debris into orbit, they modeled it as energetic enough to briefly turn both bodies into a single, vastly bloated, donut-shaped structure, part liquid, part vapor, spinning too fast and carrying too much energy to settle into an ordinary planet's shape. They gave this structure a new name, a synestia, because it did not fit any existing category of astronomical object. Inside that structure, material from the proto-Earth and material from Theia would have had time to mix thoroughly before condensing back out, first into the Earth, and then, slightly later, into a Moon condensing from droplets within the cooling, contracting remnant of the same cloud. If the model is right, the Moon and Earth are isotopically similar, not because Theia happened to resemble Earth, but because, for a brief and violent period, there was no meaningful difference between the material that would become either of them at all. Other researchers have proposed competing fixes that Theia genuinely did form from material closely resembling Earth's own to begin with, or that there were 2 separate impacts rather than one, an idea sometimes called the hit-and-run scenario, in which an early collision between the same 2 bodies failed to fully merge them, leaving Theia in a battered, slowed orbit that eventually brought it back around for a second, final collision, roughly 1 million years later. By that point, proponents of this version argue both bodies would already have exchanged enough material in the first glancing pass that the second, decisive impact simply finished combining 2 objects whose compositions had already been partly equalized beforehand. None of these explanations has been fully settled, and the synestia model itself remains one competing picture among several rather than a final answer. The giant impact remains the best available explanation for how the Moon came to exist. It is not a closed case. This is why the missing mantle problem was never simply a curiosity about one basin. If the moon's mantle could be sampled directly, rather than inferred from gravity models, and a small set of Apollo-era rock samples collected entirely from the near side, it would give the giant impact hypothesis something it had never had: a second, independent data point about what the moon is actually made of at depth and in a place far enough from previous sampling sites that contamination by later geology would be easy to rule out. The basin that this impactor carved was not just a hole, it was a probe into one of the oldest unresolved questions in planetary science, expecting a result it could not get from any sensor in orbit. All of this, the missing mantle, the burial hypothesis, the giant impact argument it quietly bears on, sat as an open question until China's lunar exploration program reached a point where landing on the far side became possible at all. The program is named, fittingly, after the goddess who is said to live alone on the moon in Chinese mythology, and each mission carries forward a small piece of the same folklore. Chang'e 1 and Chang'e 2, launched in 2007 and 2010, were orbiters built to map the lunar surface in increasing detail and rehearse the navigation needed for an eventual landing. Chang'e 3, in 2013, delivered China's first lander and first rover, Yutu-Two, to a plane on the near side, becoming the first soft landing on the moon by any nation in nearly 4 decades. Chang'e 4 was conceived, from fairly early on, as something more ambitious than a straightforward repeat of that success. Rather than land again on the familiar near side, the mission would attempt something no spacecraft from any country had ever attempted: setting down on the face of the moon that never looks back at Earth at all, where no signal could possibly reach a spacecraft directly, and where success or failure would be evident only through a relay satellite built and launched specifically to make the attempt possible in the first place. On the 7th of December 2018, a Long March 3B rocket lifted off from the Xichang Satellite Launch Center in Sichuan Province. It carried the Chang'e 4 lander and the Yutu-Two rover. Their destination was the floor of von Karman crater, a 186-kilometer basin within the northwestern quadrant of the larger basin we have been describing, named for the Hungarian-American engineer Theodor von Karman, who spent most of his career at the California Institute of Technology and became, in 1944, the founding director of the Jet Propulsion Laboratory. There is a strange piece of history folded into that name, one worth pausing on before we go any further. Among von Karman's most gifted students at Caltech was a young Chinese engineer named Qian Shuizhen, known in the West at the time as Shuishen Qian, who helped found the very laboratory von Karman would go on to direct and became one of the founding figures of American rocketry in the 1940s. A decade later, during the anti-communist suspicion that swept the United States in the 1950s, Qian was falsely accused of communist sympathies, stripped of his security clearance, and placed under years of restricted movement before eventually being deported to China in 1955, a decision an American naval official is reported to have later called one of the stupidest things the country ever did. Qian went on to become the principal founder of China's own rocket and space program, the same lineage of institutions that, 6 decades later, would design, build, and fly the very spacecraft now descending toward a crater named after the mentor he had been forced to leave behind. Neither man could have known, in 1936, when Qian was a graduate student running early rocket tests in a dry canyon outside Pasadena under von Karman's supervision, that one of their names would eventually be written onto the far side of the moon, or that the other's life's work would land a machine inside it. The site had been chosen carefully, a flat, basaltic plain that offered a safe landing, but located within the Great Basin's boundary. It was a compromise between engineering safety and scientific ambition. Some scientists had argued for a rougher site closer to the center of the basin, where the crust was even thinner and the chance of finding mantle material was higher. The mission planners chose the safer option. The rover would have to work with what it could reach. The relay satellite, Yutu-Two, had been launched 7 months earlier, in May of 2018. Its name means Magpie Bridge, taken from a Chinese folktale about a bridge of magpies that forms once a year across the Milky Way, to reunite two lovers kept apart for the rest of the year. A Lagrange point is one of a handful of specific locations in space where the combined gravitational pull of two large bodies, together with the orbital motion of an object caught between them, balances out in a way that lets a third, much smaller objects sit in a fixed relationship to both, without constantly drifting away or needing to burn fuel to correct its position. The Earth and Moon have 5 of these points between them. The second one sits roughly 65,000 kilometers beyond the far side of the Moon, on the far side of the far side, so to speak, directly along the line connecting Earth and Moon extended outward. An object placed there does not orbit the Moon in any conventional sense. It orbits the combined gravity of the entire Earth-Moon system, holding its position relative to both bodies as they continue moving together through space. Chang'e was not parked exactly at that point, which is not quite stable enough on its own for a satellite to sit at indefinitely, but in a wide, slow halo orbit looping around it, close enough to serve the same purpose while requiring only occasional, modest corrections to stay there. Chang'e was placed in this halo orbit around the second Earth-Moon Lagrange point. From that vantage point, it could see both the Earth and the far side, simultaneously the only spacecraft in history. At that point, to occupy that position, that detail is worth sitting with for a moment, because it points at something easy to forget about the place this whole story is set. The Moon keeps the same face turned toward us at all times, locked by tides into matching its rotation to its orbit, which means the far side does not occasionally see the Earth and occasionally lose sight of it the way the near side experiences day and night. The far side simply never sees the Earth at all. Not once, not briefly, not from any angle, in the entire 4.5 billion year history of the Moon. If you stood on the basin floor we have been describing tonight and looked straight up, there would be no blue marble hanging in the black sky waiting for you, the way there famously is from the near side. There would be nothing where Earth should be, ever, under any circumstances, for as long as the Moon continues doing what it has always done. Every photograph of Earth ever taken from the lunar surface Earthrise, the blue marble, all of it was taken from the near side, because the far side offers no equivalent shot to take. Chang'e, sitting quietly beyond the Moon at that particular gravitational balance point, was for a while the only thing in the solar system with a clear line of sight to both halves of that divide at once. The engineering was not trivial. If Chang'e failed, the entire mission would be lost in silence. The far side of the Moon is radio isolated from Earth. No signal can pass through 3,474 kilometers of solid rock. Every command, every data packet, every image from Chang'e 4 would have to travel from the landing site to Chang'e, and then from Chang'e to Earth. The mission team at the Beijing Aerospace Control Center had no direct line to their spacecraft. They were, in a very literal sense, talking to it through a mirror placed in space for exactly that purpose. And if the mirror cracked, there would be nothing on Earth capable of hearing the lander at all. On the 3rd of January 2019, the lander began its descent. The final phase happened too fast, and with too great a communication delay even through the relay, for any human operator to fly it by hand. The descent sequence had been programmed in advance. Every burn, every adjustment, every moment the lander would check its own altitude against the terrain below and correct its path, all of it written into the spacecraft beforehand and triggered automatically once the descent began. In the control room in Beijing, the engineers had nothing to do but watch the data arrive a little after the fact and wait to learn, the same way the rest of the world eventually would. Whether the machine they had built had landed itself correctly on ground, no human eye had ever seen up close. It fired its main engine to slow from orbital velocity, then used a series of smaller thrusters to navigate the final meters. At 10:26 in the morning, Beijing time, the lander touched down. A few hours later, the first image came back. A grey, gently rolling plain, scattered with small craters and boulders, stretching toward a horizon no human eye had ever seen from the ground. The Yutu-Two rover, named for the jade rabbit of Chinese mythology, the companion of the moon goddess Chang'e, rolled down the ramp a few hours after landing. It weighed about 140 kilograms. It was the size of a small desk, with 6 wheels, a mast carrying a panoramic camera, and 2 primary science instruments, a visible and near-infrared imaging spectrometer, and a 2-channel ground-penetrating radar. Its top speed was less than half a meter per minute. At that pace, a person walking at an ordinary stroll would lap it several hundred times over before it had crossed the length of a football pitch. It was not built for speed. It was built to look carefully at whatever it passed, for as long as it took, Its predecessor had not been so fortunate. Yutu-1, carried to the near side by Chang'e 3 in 2013, suffered a control circuit failure partway through its second lunar day on the surface and never moved again, though it survived in place, silently returning some instrument readings for years afterward. Yutu-Two's engineers had studied that failure closely before their own rover ever left the factory floor. There is a particular kind of confidence that only comes from having already watched something go wrong once and having had the chance to fix it before trying again. The lander, which stayed behind while the rover rolled away, was carrying a quieter experiment of its own. Sealed inside an 18-centimetre canister was a self-contained miniature ecosystem, built by a team at Chongqing University and stocked with cotton, potato, and rockcress seeds, alongside fruit, fly eggs and yeast, air, water, and soil enclosed together, a tiny attempt at a self-sustaining biosphere on another world. On the 7th of January, photographs sent back from the canister showed a single cotton seed had germinated. It was the first time any plant had ever grown on the surface of the moon. The sprout did not last. The canister had no heater of its own, and once the lunar night arrived 2 weeks later, the temperature inside fell to roughly 50 degrees below freezing, and the small green shoot died exactly the way any seedling on Earth would if you left it outside in a hard winter with no way to come back indoors. It is a small, slightly melancholy footnote to a mission better remembered for rocks and radar, but it is worth keeping in mind later tonight when we talk about what it might eventually take to keep something alive on that same ground for longer than a single lunar day. The rover began its slow traverse across the plain. It stopped to examine rocks. It took panoramas. It sent pulses of radar into the ground and listened for the echoes. It had no schedule to keep and know where it needed to be by a particular date. Its only job was to look, patiently, at whatever the basin floor put in front of it. And in May of 2019, less than 5 months after landing, that patience produced something specific. The rover had been driving for weeks across the basaltic plain, stopping to examine rocks, taking panoramas, sending radar pulses into the ground. The terrain was gentle, the slope barely noticeable. Ahead of it, a crater began to take shape on the horizon, first as a slight rise, then as a low rim of ejected rock, and finally as a bowl about 72 meters across, its interior in shadow, its rim littered with blocks of stone thrown up from below. The crater was young. On the moon, youth is relative. It might have formed a few million years ago, or a few tens of millions. What mattered was that it was fresh enough that its ejector had not yet been ground down into the surrounding regolith by the slow, constant rain of micrometeorites that erases sharp features over time. There is no calendar stamped on a crater, but there are reliable enough proxies for one, and the mission team had already used them before the rover ever arrived at this particular rim. A genuinely fresh crater on the moon has a sharp, well-defined edge rather than a softened, slumped one, because the slow rain of micrometeorite impacts gradually rounds off every crisp boundary it touches, the same way patient erosion rounds off a sharp stone over enough time, just without any water or wind involved in the process at all. A fresh crater is also typically surrounded by a visible blanket of bright ejecta and sometimes thin, pale rays of material flung out along its original trajectory, both of which darken and blend into the background regolith over time as space weathering slowly works on them. None of this gives you an exact number of years. What it gives you is enough confidence to say that a crater looks recent rather than ancient, and that any material sitting on its rim has not yet had the time to be buried again or weathered past recognition. This particular crater, by every visual measure the team could apply, looked recent enough to be worth a closer look. The rocks on its rim were angular, fractured, their surfaces clean. They had come from depth, and depth, in this part of the basin, was the whole point. The rover's spectrometer sits on its mast. It is a small instrument, its aperture only a few centimeters across, and it works by measuring the intensity of reflected sunlight across a range of wavelengths from the visible blue through the near-infrared. When sunlight strikes a mineral, certain wavelengths are absorbed by the chemical bonds inside its crystal structure, and the pattern of what gets absorbed is a fingerprint. Olivine absorbs broadly near 1 micrometer. Pyroxene absorbs at 2 narrower bands close to 9/10, and 1.9 micrometers. Plagioclase feldspar, the dominant mineral of the lunar crust, absorbs at a different wavelength again, and far more weakly. The spectrometer does not take a picture in any conventional sense. It takes a reading, a curve of brightness against wavelength, its dips and peaks encoding the mineralogy of whatever it is pointed at. The rover stopped near the crater's rim and pointed its spectrometer at one of the ejected rocks. The reading came back to the team at the Beijing Aerospace Control Center and the scientists at the National Astronomical Observatories of the Chinese Academy of Sciences, who watched the spectral curve appear on their screens. There is a particular kind of silence that falls in a room when data arrives that is not just interesting but definitive, not the silence of confusion, but the silence of recognition, the moment before anyone speaks, when everyone present understands that what they are looking at has resolved a question that has been open for longer than some of them have been alive. The spectrum showed two deep absorption features. The first was a paired set of troughs near 9/10 and 1.9 micrometers, the signature of low calcium pyroxene. The second was a broad absorption centered near 1.05 micrometers, the signature of olivine. Together, the two minerals indicated a rock type called harzburgite, or possibly hersolite, depending on the exact ratio between them. Both names for rock built almost entirely from olivine and pyroxene crystals locked together with barely any of the lighter minerals that dominate a crust, the geological equivalent of a rock made almost purely from the heaviest ingredients available, with everything lighter already skimmed off the top long before it crystallized. Geologists studying the Earth's own mantle, brought up occasionally in volcanic eruptions or exposed at a handful of unusual sites where deep crust has been thrust up to the surface, use these same two names for the same reason. Those sites have a name of their own: ophiolites, places where a slab of ancient ocean floor and the mantle rock beneath it has been folded upward by plate tectonics and laid bare at the surface, rather than buried back down the way oceanic crust almost always eventually is. The tablelands in Grossmorn National Park, on the west coast of Newfoundland, are one of the more accessible examples, a barren, rust-orange landscape so different from the forests surrounding it that early visitors assumed nothing could grow there, which is more or less true because the rock itself is mantle material, harzburgite among it, sitting in the open air where almost anyone can walk up and place a hand directly on it. Finding the same mineral signature on the moon is the equivalent of recognizing a familiar word in an unfamiliar language. The underlying chemistry of planetary interiors, it turns out, does not vary all that much from world to world, however differently the surfaces above them might end up looking. Both are mantle rocks. Neither has any business sitting on the surface of a body whose crust is built almost entirely from an orthosite. Li Chunlai, the director of the key laboratory of lunar and deep space exploration at the National Astronomical Observatories and the lead scientist for Chang'e 4's scientific payload, is not a man given to dramatic public statements. In interviews, he speaks carefully and precisely, with the measured tone of someone who knows the data will outlast the words used to describe it. When he saw the spectrum from the small crater, he used a single word: unambiguous. The detection was unambiguous because the signature of olivine and low calcium pyroxene is distinct from anything found in the lunar crust. The crust is dominated by a northosite, a rock that forms when a magma ocean cools and its lighter minerals float to the top. Plagioclase has a much weaker absorption feature at a different wavelength entirely. The spectrum from the crater rim was not a subtle variation on a crustal theme. It was a different song altogether. In the middle of May 2019, the journal Nature published the team's findings under a title written with the same restraint typical of the man who led the work: an initial spectroscopic identification of mantle-derived material on the lunar far side. The body of the paper laid out the evidence, the absorption bands, the match to laboratory spectra of terrestrial mantle rocks, the geological context of the crater, and the interpretation that the impact had excavated material from a buried layer of ejecta, originally thrown out by the basin-forming event itself. The missing mantle problem, the puzzle that had persisted through Clementine, Lunar Prospector, Chandrayaan-1, Kaguya, and the Lunar Reconnaissance Orbiter, finally had an answer. The answer was not that the mantle was absent, it was that it had been hidden. The impact had indeed excavated the moon's deep interior and scattered it across the basin floor. just as the burial hypothesis predicted. But in the 4 billion years since, lava flows had covered much of it, and the relentless rain of smaller impacts had churned the surface into a fine regolith that masked the mantle's chemical signature from anything looking down from orbit. Only a fresh, small impact, one that punched through the overlying basalt and regolith and threw up intact chunks of the buried material, could reveal what lay beneath. The 72-metre crater was exactly such an impact. It was a natural drill core, a window into the moon's interior that had been opened recently enough that the exposed rocks had not yet been erased by space weathering, and Yutu-Two had been in the right place at the right time to look through it. This mattered beyond the basin itself. If the impact had truly excavated the lunar mantle, then this was the closest anyone had come to sampling directly the material the giant impact hypothesis depends on. A second, independent window into what the moon is built from at depth, far from every Apollo landing site and far from the assumptions baked into decades of gravity modeling. It did not settle the argument about Theia. The isotopic puzzle remained exactly as stubborn as before, but it gave the argument something it had not had since the 1970s: new material, from a new place that no one had had to infer. The rover did not linger at the crater. It took its readings, transmitted its data, and continued its traverse. There were other craters to visit, other rocks to examine. The spectrometer had answered one question with unusual clarity. It could not answer what came next, what the impact had done, not just to the rock sitting on the surface, but to everything still buried beneath the rover's wheels. The mission had originally been designed to last 3 months, 1 lunar day, followed by the 2-week lunar night that inevitably follows it. Nobody on the team, in May of 2019, knew for certain how long the rover would actually survive that night, let alone many of them in succession. The lunar night is brutal in a way that is hard to translate into ordinary experience. 14 Earth days of continuous darkness, temperatures falling to around -190 degrees Celsius, with no sunlight at all to keep the rover's batteries charged or its electronics from freezing solid. Yutu-Two carried a radioisotope heater unit, a small sealed source of warmth generated by the steady radioactive decay of plutonium-238, just large enough to keep its most sensitive components above the temperature at which they would simply stop functioning. The thermal stress of repeatedly cycling between the heat of the lunar day and the deep cold of the lunar night is punishing on hardware never designed to survive it more than a handful of times, and every single sunrise carried a real chance that the rover would not wake up. It kept waking up anyway. Month after month, lunar day after lunar night, it passed its 3-month design life and kept going. As of the most recent reports available, Yutu-Two has logged well over 70 lunar days of activity and driven a little more than 1.5 kilometers across the basin floor, making it, by a wide margin, the longest-lived rover ever operated on the surface of the moon. Its own predecessor, Yutu-One, had managed 972 days before finally falling silent for good. By the standard the field itself uses to measure success, Yutu-Two had already outlived every expectation placed on it before it ever took its first reading from that small crater's rim. What it found down there was not fire, it was silence. Ground-penetrating radar is not, in itself, exotic technology. Archaeologists use a version of the same instrument to map buried walls and foundations without digging a single trench first. Civil engineers use it to check for voids and pipes underneath a road before deciding where to drill. The principle is the same. In every case, send a radio pulse downward, listen for what bounces back, and use the timing and strength of the echo to infer what is sitting underneath ground you cannot otherwise see into. What makes the version riding on Yutu-Two's underside unusual is not the physics. It is the fact that nobody had ever pointed one of these instruments at the floor of an alien basin before. 4 billion years deep in a record no rain or root system had ever disturbed. The radar instrument on Yutu-Two is a 2-channel system. The high-frequency channel operates at 500 MHz, sending short pulses into the ground and listening for reflections from boundaries as little as a few centimeters apart. It sees fine detail, but only down to a depth of about 12 meters. The low-frequency channel, at 60 MHz, penetrates deeper down to about 40 meters but with lower resolution. Together they build a vertical profile of the ground beneath the rover's wheels, assembled from the time delay of each radio echo. It is the closest thing we have to an ultrasound of the moon's shallow subsurface, and it was asking a different question than the spectrometer had. The spectrometer asked what a single rock was made of. The radar asked what had happened here, in sequence, over the past 4 billion years. In 2020, Li Chunlai's team published the first comprehensive analysis of the radar data in the journal Science Advances. What they found was a stratigraphy, a sequence of buried layers that told a story of repeated, smaller-scale violence stacked on top of the original catastrophe. The top 12 meters were relatively uniform, the reflections weak and featureless, indicating a material of consistent density with no sharp internal boundaries. This was the modern regolith, the crushed, gardened surface layer produced by billions of years of micrometeorite bombardment. On the moon, there is no wind, no rain, no tectonic activity to turn over the soil, but there is a constant, gentle rain of particles the size of dust, grains, and sand, traveling at tens of kilometers per second, each one shattering the surface rocket strikes and producing a fine powder that accumulates, year on year, with nothing to disturb it. Below 12 meters, the low-frequency channel revealed something more structured, a sequence of alternating coarse and fine layers, extending down to the limit of its penetration at about 40 meters. The coarse layers produced strong, irregular reflections, chaotic on small scales, indicating a jumble of rocks and boulders. These were interpreted as ejector blankets, sheets of debris thrown outward by impact somewhere nearby. The fine layers between them were paleo-regolith, ancient surfaces that had themselves been exposed long enough to develop their own thin coating of dust, gardened by micrometeorites, before the next nearby impact buried them again under a fresh blanket of debris. An impact occurs. The landscape is draped in a sheet of rubble. The surface sits exposed for millions, sometimes hundreds of millions of years, slowly accumulating its own fine regolith. Then, another impact happens nearby, and the cycle repeats. The radar was not seeing one event. It was seeing many events, stacked in time like the pages of a book nobody had opened in billions of years. The basin floor, in other words, was not a single uniform lava plain. It was a palimpsest, a surface written and rewritten by a long series of smaller, more recent craters, each one excavating material from a slightly different depth and scattering it across what had already been scattered before. 2 years later, in 2022, a team led by Jianqing Feng published a more detailed reanalysis of the same data. They focused on the deeper portion of the profile, below about 17 meters, where they identified a particularly strong, continuous reflecting boundary that they interpreted as a buried crater floor, the original surface of a much older impact, completely sealed beneath later ejecta. The material below this boundary had different radar properties, more homogeneous, less reflective, possibly a mixture of impact melt and deep-seated rock that had never been reworked by later gardening. Feng's team suggested this material might be related to the mantle-derived rocks the spectrometer had already found at the surface, that the 17-meter boundary might mark the very layer of buried ejecta that the fenned, small crater nearby had finally punched through. The interpretation was careful, and it was contested. Radar measures density contrasts, not chemistry. A reflection tells you that two materials are different from each other. It does not tell you what either of them is made of. Some Western researchers argued that the deep reflection could just as easily come from a contact between different basalt flows within the basin's lava fill, rather than anything related to the mantle. The ambiguity is genuine, and it remains unresolved. But what the radar showed without any ambiguity at all was that the subsurface was not a uniform slab of basalt. It was structured, layered, ordered in time, a physical record of events that a future mission, with a drill rather than a radar antenna, could sample directly, layer by layer, to reconstruct the impact history of the Earth-Moon system, with a precision no orbital survey could match. This kind of preservation is owed almost entirely to the Moon's stillness. On Earth, wind, rain, and plate tectonics erase the record of most impacts within a few million years. There are very few rocks left anywhere on our planet old enough to remember the era this basin formed in. We will come back to exactly how few and how strange the ones that remain actually are. On the Moon, there is no equivalent erosion. The only processes that modify the surface are impact, and in the distant past, volcanism. And the volcanism mostly shut down more than 1 billion years ago. A crater formed 4 billion years ago still looks like a crater. A layer of ejecta buried 3 billion years ago is still, structurally, a layer of ejecta. The moon is a geological fossil, and the far side never resurfaced the way the near sides Maria were, never subject to the faint tidal flexing the near side experiences from Earth's pull, is the most pristine half of that fossil. Every impact violent enough to scar the moon also struck the Earth, and because the Earth is a larger target with stronger gravity, it was hit more often and by larger objects than the moon ever was. The layers beneath Von Karman crater are not only a record of the moon, they are a record, by extension, of our own planet's history, preserved in the only archive that survived. And there is a second kind of preservation at work here, one that has nothing to do with rock at all. It is not in the layers underfoot, it is in the air that does not exist. The far side of the moon is the only place in the inner solar system naturally shielded from all terrestrial radio noise. The moon's bulk 3,474 kilometers of rock blocks every transmission from Earth. A mobile phone on the lunar surface would be one of the brightest radio sources in the sky, as seen from the near side, but on the far side it would be silent to any receiver on Earth. The shielding is absolute. This quiet is not just deep. It is orders of magnitude deeper than the quietest place on Earth. The best radio quiet zones on our planet, the National Radio Quiet Zone in the United States, the Karoo Desert in South Africa, the Murchison region in Western Australia, still contend with the ionosphere, with distant transmitters, with the faint hum of power lines and satellites passing overhead. On the far side, none of that exists. There is no ionosphere to distort anything. There are no transmitters, no power lines, no satellites of our own making. There is only rock, vacuum, and cold. That silence holds something that has been traveling for more than 13 billion years, trying to reach somewhere capable of listening for it. In the standard model of cosmology, the universe began in a hot, dense state and expanded. For the first 380,000 years, it was so hot that matter existed as a plasma, electrons and protons moving independently, constantly scattering photons in every direction. The universe was opaque. Light could not travel freely. It was absorbed and re-emitted, in a dense fog of charged particles that had nowhere clear to go. Then, as the temperature dropped below about 3000 Kelvin, electrons and protons combined to form neutral hydrogen atoms, and the fog cleared. Photons that had been trapped inside the plasma were suddenly free to travel, and they have been traveling ever since, stretched by the expansion of space into the microwave band. We detect them today as the cosmic microwave background, the faint glow that fills every direction of the sky. It is the oldest light in the universe, but it only marks the moment the fog cleared. For a long stretch of time after that, there were no stars at all. The first ones did not ignite until roughly 150 million years after the beginning, perhaps later. The period between the clearing of the fog and the ignition of the first stars is called the Dark Ages. It is the only epoch in the entire history of the universe from which no electromagnetic signal has ever been directly detected. Picture that period for a moment, not as an absence but as a place. There is no light anywhere, because there are no stars yet to make any. There is only neutral hydrogen gas, filling every direction evenly, at a temperature slowly falling as the universe stretches around it. If you could somehow be there, suspended in that gas with nothing else to see, you would not be in darkness exactly, you would be inside the only thing that existed, with no edge, no horizon, and nothing yet built that could cast a shadow. Every hydrogen atom in that gas, everywhere, is doing the same quiet thing, occasionally flipping the spin of its single electron and releasing, in the process, a photon with a wavelength of 21 centimeters. It is the most famous spectral line in radio astronomy, and during the Dark Ages, it was being sung by the entire universe at once, in a single uniform note, with nothing yet alive to hear it. That note has been stretched by the universe's own expansion. What was emitted at 21 centimeters has been redshifted to much longer wavelengths, the exact amount depending on when the photon was released. For a signal from the middle of the Dark Ages, the wavelength has been stretched to several meters frequencies in the tens of megahertz, a part of the radio spectrum that is nearly impossible to observe from the ground. The ionosphere blocks most of it outright, and what little gets through arrives swamped by the background roar of our own civilization's radio transmissions. A signal from the Dark Ages, by the time it reaches Earth, has the strength of a whisper. On Earth, that whisper is drowned by a stadium crowd. On the far side of the Moon, there is no stadium crowd. There is no ionosphere, no transmitters, nothing competing for the same narrow band. Somewhere in the low-frequency radio spectrum, between roughly 10 and 100 megahertz, sits a faint, structured signal, a map of the universe as it existed before the first star ever shone. It is the only direct observational window we know of into an epoch that is otherwise, by definition, dark. The idea of using the far side as a radio observatory is not new. It was proposed as early as the 1960s, once it became clear that the Moon's bulk blocks Earth's radio noise completely. But the engineering challenge has always been formidable. An array of antennas spread across hundreds of meters or more, each one precisely positioned, powered through a 14-day lunar night at temperatures of -190 degrees Celsius, with the data relayed back to Earth through exactly the kind of satellite link that made Chang'e 4 possible in the first place. A small step toward that dream was taken in 2018. Yutu-Two, the same relay satellite supporting Chang'e 4, carried a technology demonstration developed jointly by Dutch and Chinese teams, 3 monopole antennas, each 5 meters long, designed to unfurl in space and listen to the low-frequency radio sky from the satellite's unique vantage point. The deployment did not go smoothly. One antenna extended correctly, the other 2 remained stuck, partially folded, and the team behind the instrument, led by Mark Klein-Walt of Radboud University in the Netherlands, spent months troubleshooting a mechanism they could not physically reach, hoping that the simple expansion and contraction of metal as the satellite moved between sunlight and shadow might eventually free what commands alone could not. Eventually, it did, enough to begin taking data. The instrument recorded the low-frequency radio emission from the Milky Way itself, a faint background hiss from cosmic ray electrons spiraling in the galaxy's magnetic field. It did not detect the Dark Ages signal that would require something far larger and far more sensitive, deployed directly on the surface rather than orbiting above it. But it proved the underlying idea worked. A receiver sitting in the far side's radio shadow really could hear things that no instrument on Earth ever would. Several full-scale concepts now exist on paper. One, proposed by Chinese and European scientists, would place a swarm of small satellites in orbit around the Moon, using the far side's shadow as a shield to map the entire low-frequency sky. The idea behind using a swarm, rather than one large dish, is interferometry, combining the signal received by many small, widely separated antennas as though they were all part of one much larger instrument, with an effective resolving power that depends on the distance between the farthest apart satellites rather than the size of any single one of them. Spread a swarm of small, cheap satellites widely enough across lunar orbit, and you can approximate the resolution of a single dish far too large to ever launch in one piece. Another concept, studied by NASA under the name Far-Side Array for radio science investigations of the Dark Ages and exoplanets, would place hundreds of dipole antennas directly on the surface itself, spread across several kilometers of basin floor, listening for the Dark Ages signal with a sensitivity that only a large, stationary, ground-based array could provide. Neither has been funded for an actual mission yet. The engineering remains difficult, and the cost is high. But the far side's silence is a resource in the fullest sense of the word, and resources of this kind tend not to stay unclaimed for long. Whoever eventually builds the first working array there will own, for some years at least, the only direct window onto the universe's darkest and earliest chapter, and everything that chapter can tell us about how the rest of cosmic structure first began to form. The silence of the far side carries a signal from the universe's infancy. It also carries a record of something much closer to home, the planet most of us are sitting on right now, while we listen. The same stillness that preserves the layers beneath von Karman crater preserves the memory of what those layers actually mean. An impact carrying 500 million times the energy of the largest weapon humanity has ever built did not happen to a planet that was simply standing nearby. It happened to the Moon, which orbits the Earth at a distance of roughly 380,000 kilometers, close enough that whatever struck one body was, statistically, almost certainly part of the same population of debris crossing the other body's path as well. The Earth is a much larger target than the Moon, with considerably stronger gravity pulling in anything that came close. Its gravitational cross-section is roughly 20 times the Moon's. For every object that struck the lunar surface during this era, something on the order of 20 similar objects struck the Earth. An impact on the scale of the one that carved this basin did not happen to the Moon and somehow spare its neighbor. The odds of that, across the hundreds of millions of years this period lasted, are effectively zero. What would an impact like that have done to a planet with oceans and an atmosphere, rather than a bare, rocky surface? The basin-forming event melted and vaporized thousands of cubic kilometers of rock on the Moon alone. On Earth, with stronger gravity holding everything closer and an atmosphere and ocean to absorb and redistribute the energy, the result would have been worse, not better. A transient crater at least 1,000 kilometers across, punching through crust and into mantle, molten rock thrown into orbit, some of it falling back as a burning rain, some of it escaping entirely. An atmosphere superheated past anything resembling breathable air. Oceans flashed into steam. For months, perhaps years afterward, the surface would have been a roiling inferno under a sky glowing with the heat of recondensing rock vapor, the ground-level pressure, alone enough to sterilize anything still clinging to a foothold. And this did not happen only once. The cratering record on the Moon, not just this one basin, but hundreds of smaller large basins, and many thousands of smaller craters besides, implies that the Earth was struck by thousands of objects larger than 10 kilometers across during the Hadean, and dozens larger than 100 kilometers. Whether there was a single discrete spike in that bombardment rate around 3.9 billion years ago, a period sometimes called the Late Heavy Bombardment, remains genuinely debated among specialists. But even setting the spike question aside, the background impact rate during this era was orders of magnitude higher than it is today. The Earth, for the first several 100 million years of its existence, lived inside a shooting gallery with no walls. The evidence for any of this, on Earth itself, is almost entirely gone. The oldest known rocks on our own planet are the Acasta gneiss, found in the Northwest Territories of Canada, dated to about 4.03 billion years old. Even they are metamorphic, heated, squeezed, and chemically altered by later geological processes, and they date from a time when the worst of the bombardment was very likely already over. Before that, there is nothing, no surviving rock at all, anywhere on Earth, from the first 500 million years of the planet's existence. It is a complete blank in the geological record. The only witnesses from that lost period are zircons, tiny crystals of zirconium silicate that form inside granitic magmas and are extraordinarily resistant to later alteration. The oldest known zircons, recovered from the Jack Hills region of Western Australia, are up to 4.4 billion years old. They are smaller than a grain of sand, and they carry chemical and isotopic clues about the conditions under which they crystallized. The oxygen isotope ratios in some of these zircons suggest liquid water was already present on the Earth's surface by that point remarkably early, and surprisingly cool, given everything we have just said about the impact rate at the time. The zircons seem, at first glance, to contradict the picture of a permanently hellish surface. But zircons are survivors, and survivors are not always representative. They may record brief, local windows of relatively stable conditions opening up between successive sterilizing impacts. The bombardment was intense, but it was not constant. Between the largest collisions, the surface may have cooled enough for water to condense and for the first scraps of a stable crust to begin forming, before the next major impact reset the clock entirely. This is also why the lunar record matters so much to people who study the early Earth. If you know the impact rate on the Moon, you can calculate the impact rate the Earth experienced over the same period. If you know when the Moon's large basins formed, you know, roughly, when the Earth was most likely to have been sterilized in turn. The Moon is a fossil of the Hadean, and the far side never resurfaced by Maria the way the near side was, never even seen by a human eye, until 66 years ago is the most pristine surviving part of that fossil. This one basin is the single most important feature in it. The largest, deepest, oldest impact structure we can study directly, recording a single event so violent it would have devastated the Earth as severely as it nearly devastated the Moon. It is not just a hole in the ground, it is a sample return site, waiting to be properly read. Earth has no equivalent site of its own left, standing anywhere on its surface. Whatever this basin can tell us about that lost period of our own planet's history, it will have to tell us, because nothing comparable has survived back home to ask directly. A number worth sitting with. The asteroid that struck the Yucatan Peninsula 66 million years ago, ending the Cretaceous and clearing the way for the eventual rise of mammals, was perhaps 10 to 15 kilometers across, roughly the same size as the impactor we have already discussed at the start of tonight's story. Scale that same comparison up by a factor of about 20 in diameter and roughly 8,000 in mass, and you arrive back at the basin-forming impact itself, with an energy release something like 10,000 times greater than the one that ended the dinosaurs. The Chicxulub impact eliminated about 75% of all species on Earth at the time. An impact at the scale this basin represents would not stop at most species. It would reach the entire surface biosphere, down to whatever single-celled organism was hiding furthest from the light. Oceans boiled away, atmosphere stripped or superheated past survival, crust melted, no refuge anywhere on the surface, and very little margin underground either. This is not a hypothetical scenario. It happened, on this scale or close to it, more than once, during the Hadean. The evidence for it is written on the face of the Moon, in basins exactly like this one. Nothing about the object that carved this particular basin was aimed at anything. It was a piece of leftover planetary construction material, following an orbit shaped by gravity and the accidents of its own formation, and it happened to cross paths with a smaller world at a moment when both of them were simply where physics had put them. The Moon did not do anything to deserve being struck, any more than it would have done anything to deserve being missed. The same is true of whatever struck the Earth on a comparable scale during the same era, and of every smaller impact that has struck either body since. Indifference, in this very literal sense, is not a metaphor. It is closer to a description of an orbital mechanics problem that happened to intersect with a planet. Planetary scientists tend not to discuss this particular implication in public very often, not because anyone is hiding it. It is simply standard background knowledge in the field, the kind of fact you live alongside rather than announce at every opportunity. The way a geologist in California lives alongside the knowledge that a major fault line nearby will eventually slip. You build the models, you map the basins, you go back to your work, because there is nothing especially useful to do with the knowledge beyond understanding it as clearly as possible. The bombardment has not stopped completely, even now. The solar system still contains a population of near-Earth objects, asteroids and comets whose orbits cross our own. None of them is anywhere close to 200 kilometers across. The largest known object of that kind is roughly 30 kilometers. But objects large enough to cause regional devastation, and a smaller number large enough to cause effects felt across the whole planet, do exist, and the survey work needed to catalogue all of them, especially the smaller ones, remains incomplete. The Oort cloud, the distant shell of comets surrounding the solar system at distances of up to a light year, holds an unknown number of additional objects, occasionally nudged inward by the gravity of a passing star. Nothing the size of the basin-forming impactor remains in an orbit that crosses the Earth's path. That population of leftover building material was used up, mostly during the Hadean itself. But smaller objects, on the scale of the one that struck the Yucatan, exist in real numbers and have struck the Earth many times since, and will again, not whether, when. There is a strange complication folded into all of this violence, one that planetary scientists have spent a long time untangling. The same bombardment capable of sterilizing a planet outright also appears to have been the main route by which a young rocky world like Earth acquired much of its water and its carbon-based chemistry in the first place. Models of early planet formation generally suggest the inner solar system formed too hot and too dry for much water to have condensed directly out of the material that built Earth's crust and mantle. A meaningful fraction of what eventually became our oceans, on most current models, likely arrived afterward, carried in by comets and water-rich asteroids during this same chaotic era of impacts, a process sometimes called the late veneer. The same kind of collision capable of boiling an ocean away in one instance may, in countless smaller instances scattered across the same few 100 million years, have been quietly delivering the raw material for the next ocean to form. Violence and habitability, on the available evidence, were not opposites during this period. They were, uncomfortably, the same process, just observed at different scales and different moments, and untangling exactly how much of Earth's water arrived this way, rather than some other way, is itself one of the more contested open questions on the unknowns list we will return to a little later tonight. The Far Side Basin does not answer that question. It simply records, with unusual clarity, what an answer looked like the last time the scale of impact was at its very worst, and reminds anyone willing to look that the calm we currently live inside is recent by the standards of the solar system's own history, and not in any sense guaranteed to last by default. But this is not only a story about violence in the deep past. The same basin that records the worst of that violence also borders something that has nothing to do with destruction at all. At the southern edge of the Great Basin, where its rim rises toward the pole, there are craters whose floors have never once seen sunlight. The Moon's rotation axis is tilted only about 1.5 degrees relative to the plane of its orbit. On Earth, a tilt of roughly 23.5 degrees gives us seasons sunlight shifting between hemispheres over the course of a year, warming first one pole and then the other. On the Moon, there are no seasons at all. The sun circles low on the horizon at the poles, never climbing more than a few degrees above it, and any depression deep enough to sit permanently in the shadow of its own rim stays dark, in a literal sense, forever. These are called permanently shadowed regions. Some are crater floors, some are narrow clefts and crevices, some are simply the south-facing slopes of ridges that the sun's shallow arc never manages to clear. What they share is temperature. In that permanent darkness, with no atmosphere to carry heat and no sunlight ever reaching the ground, temperatures can fall to around 30 Kelvin colder than the surface of Pluto, within a few tens of degrees of absolute zero itself. At those temperatures, water ice is stable for billions of years. It does not sublimate away. It does not migrate. It simply stays exactly where it landed, molecule by molecule, slowly accumulating from cometary impacts and solar wind interactions over the entire age of the solar system. These craters are cold traps, and they have been collecting water for most of that history. The first hints came from a mission designed, in part, to crash. In 1994, the Clementine Orbiter, a joint project between NASA and the Ballistic Missile Defense Organization, originally built to test sensors intended for missile tracking, mapped the Moon at multiple wavelengths and, in passing, bounced a radio signal off the permanently shadowed floor of Shackleton Crater near the South Pole. The reflection it received back on Earth showed characteristics consistent with water ice, though the result was suggestive rather than conclusive. Rough terrain alone can produce similar signals. In 1998, Lunar Prospector carried a neutron spectrometer that measured the energy of neutrons reaching it from the lunar surface. Neutrons produced when cosmic rays strike atoms in the regolith, and slowed more effectively by hydrogen than by almost anything else. Over the lunar poles, the spacecraft found a significant suppression of medium-energy neutrons, tightly correlated with the permanently shadowed regions. It was, again, suggestive of abundant hydrogen, and therefore plausibly water, but not yet definitive proof. The definitive answer came in October of 2009, from a mission with a design simple enough to describe in one sentence: throw something heavy at a permanently shadowed crater, hard, and watch what comes up. The Lunar Crater Observation and Sensing Satellite directed a spent Centaur rocket stage, weighing about 2,300 kilograms, into Chang'e Crater near the South Pole, while a trailing shepherding spacecraft flew through the resulting debris plume to analyze its composition, before crashing into the surface itself a few minutes later. The Centaur struck at a speed of roughly 2.5 kilometers per second, excavating a crater 20 to 30 meters across and throwing a plume of material more than 10 kilometers above the surface. The impact itself was watched by an unusually large audience for a planetary science event broadcast live, with telescopes on Earth and in orbit, all trained on the same patch of permanent shadow, waiting for a visible flash to confirm the moment of impact. No dramatic flash arrived. The Centaur stage struck inside a crater deep enough that the plume rose mostly hidden from direct view, and the first wave of public reaction afterward was, if anything, mildly disappointed. A quiet thump rather than the fireball some coverage had been quietly expecting. The actual result took weeks of careful spectral analysis to confirm, far less photogenic than a flash but considerably more useful. Anthony Colaprete, the mission's principal investigator at NASA's Ames Research Center, led the team that spent the following weeks combing through the data the plume had produced. About 5.6% of the ejected material, by mass, turned out to be water ice alongside other volatiles, including carbon monoxide, carbon dioxide, ammonia, and methane. When the result was confirmed, Colaprete described the team as ecstatic and said multiple independent lines of evidence, drawn from both the high-angle vapor plume and the lower ejector curtain, agreed with each other. It is a small, ordinary word for a discovery that quietly reorganized an entire field's priorities, but it was the right one. The permanently shadowed craters at the lunar poles were not dry. They were cold, dark reservoirs of exactly the raw materials that life requires, and that any sustained human presence beyond Earth would eventually need. The implications took a few years to fully settle in, but once they did, they reshaped everything. Water is heavy, and every kilogram of it launched from Earth costs tens of thousands of dollars in fuel and engineering. Water available on the lunar surface changes that calculation completely. Split by electrolysis into hydrogen and oxygen, it becomes both breathable air and rocket propellant. Water on the moon turns the moon from a destination into something closer to a filling station, a place to restock before going somewhere else entirely. Shackleton Crater, straddling the rim of the Great Basin at the lunar South Pole, is about 21 kilometers across and roughly 4 kilometers deep. Its rim sits in near-permanent sunlight, illuminated more than 80% of the year at some points, making it an excellent site for solar power generation. Its floor sits in permanent darkness. A base built on Shackleton's rim could draw on both. Continuous sunlight for power, just a few kilometers of gentle slope away from permanent shadow for water extraction. The combination is unusual enough that Shackleton has become one of the most studied and most contested pieces of real estate anywhere in the solar system. The Lunar Reconnaissance Orbiter, launched in 2009 and still operating, has mapped the distribution of hydrogen at both lunar poles with steadily increasing precision. Its neutron detector instrument has confirmed that the hydrogen is concentrated almost entirely within the permanently shadowed regions, and current estimates range from hundreds of millions to billions of tons of water ice across the two poles combined. The exact figure is uncertain. Neutron spectrometry only sees the top meter or so of surface material, and the depth distribution below that remains unknown. But even the lower bound is enough to sustain a lunar outpost more or less indefinitely. A second instrument on the same orbiter, a thermal radiometer called Diviner, approached the same question from a completely different direction, simply measuring surface temperature across the entire moon in extraordinary detail, rather than looking for hydrogen directly. Diviner's maps confirmed just how cold the coldest permanently shadowed floors actually get, and in doing so, identified specific candidate craters likely to be the very best cold traps at either pole places where, on the strength of temperature alone, water ice should be most stable and most likely to have survived in useful quantities. Those temperature maps, layered against the earlier neutron data, are part of what eventually narrowed the search down to specific named targets, like Cabeus and Shackleton, rather than leaving the entire South Pole as one large, undifferentiated region of vague promise. This discovery has reordered the priorities of nearly every space agency with lunar ambitions. The South Pole, rather than the historically familiar near side, is now the focus of almost every mission currently being planned. NASA's Artemis program intends to land astronauts there within the decade. China's own next step is Chang'e 7, expected to launch later this year, aimed squarely at the illuminated rim beside Shackleton Crater itself. The mission's design is unusually elaborate for a single launch: an orbiter, a lander, a rover, and a small hopping probe carrying a dedicated water molecule analyzer, built specifically to leap from the sunlit rim down into the permanent darkness nearby, take a direct reading inside a permanently shadowed crater, and confirm what orbital instruments have so far only inferred from a distance. A second mission, Chang'e 8, is planned for around 2028, intended to test whether lunar soil could realistically be three-dimensionally printed into solid building material on-site, a small, practical step toward an actual structure standing on that ground, rather than just a flag and a set of footprints. Together, the two missions are meant to form the working foundation of China's planned International Lunar Research Station. Russia, India, Japan, and the European Space Agency all have South Pole missions of their own at various stages of planning, in various states of partnership or rivalry with either the American or the Chinese-led effort. The lunar South Pole has become, in the 2020s, something close to what the near side was in the 1960s, the place nations go to demonstrate that they can. The word claims is legally delicate here, and worth being precise about. The Outer Space Treaty of 1967, ratified by both the United States and China, prohibits any nation from asserting sovereignty over a celestial body. It does not prohibit the extraction and use of resources found there. The Artemis Accords, a set of agreements led by the United States and signed by more than 30 nations as of 2024, explicitly affirm the right to extract and use space resources under that framework. China and Russia have not signed the accords. They are developing a parallel framework of their own, the International Lunar Research Station, envisioning a permanent base at the South Pole with a smaller but steadily growing set of international partners. What results is a quiet, high-stakes competition that does not resemble the Cold War space race. In its shape, there is no single finish line, no flag-planting moment that settles anything outright, but is nonetheless a real competition over infrastructure, presence, and the practical capacity to operate somewhere that has become, almost overnight, strategically valuable. The far side, with its radio silence and its exposed mantle, is a scientific prize. The South Pole, with its ice and its sunlight, is an economic and strategic one. The two sit close enough together, geographically, that the missions sent to study one will very likely shape the missions sent to claim the other. A provision of United States law, first enacted in 2011 and known as the Wolf Amendment, prohibits NASA from engaging in direct bilateral cooperation with China without explicit congressional approval, a restriction originally driven by concerns over technology transfer and human rights. In practice, it has produced two largely separate lunar programs, one organized around the United States and its Artemis partners, the other around China and its International Lunar Research Station partners. Scientists in both countries still collaborate informally where they can. Data from Chang'e 4 has been published openly, and researchers in the United States have analyzed it without restriction. But joint missions, shared hardware, and coordinated planning remain legally difficult and politically sensitive, a structural echo of the separate programs the United States and the Soviet Union once ran, though the underlying stakes today are different. The original space race was driven mostly by prestige and missile technology. What is being contested now is more tangible specific resources and specific strategic positions that will likely shape human activity in space for the rest of the century. And yet, for all the calculation involved, the single most valuable thing the far side has produced so far is not water or radio silence or any strategic advantage. It is a few kilograms of rock and soil. In 2024, China brought them home. Chang'e 6 launched on the 3rd of May, 2024, from the Wenchang Space Launch Site on Hainan Island, built on the architecture of Chang'e 5, which had successfully returned samples from the near side 4 years earlier. By this point, the original Yutu-Two satellite had been joined by a successor, Yutu-Two, launched a few months earlier, specifically to support Chang'e 6, and the missions expected to follow it a sign of how thoroughly the far side had shifted in the space of 5 years, from a place reachable only through one improvised relay link to a destination important enough to justify dedicated, permanent communications infrastructure of its own. The mission comprised 4 separate components: an orbiter, a lander, an ascent vehicle, and a return capsule, and its destination was Apollo Crater, a 537-kilometer basin within the larger one we have been following all night, named by international convention rather than any connection to the American program of the same name, after the Apollo lunar exploration missions. Mission planners narrowed the search to this site after years of orbital reconnaissance, specifically because its floor combines two things rarely found together: a relatively young, smooth basaltic plain safe enough to attempt a landing on, sitting directly above older ejecta, thought to contain material excavated from the moon's deep crust and upper mantle. A site with one of those qualities but not the other would have been either too dangerous to land on or scientifically far less interesting once they got there. The mission profile left no room for error. The lander would touch down, drill into the surface, scoop additional soil from around it, and load both into a container on the ascent vehicle. The ascent vehicle would then lift off from the lunar surface on its own, rendezvous with the orbiter automatically, and transfer its sample container before being discarded. The orbiter would carry that container home, releasing the return capsule for a ballistic re-entry and parachute landing. Every single step had to work the first time. There was no backup plan if any one of them failed. On the 1st of June, 2024, the lander separated from the orbiter and descended to the floor of Apollo crater, the entire sequence pre-programmed and executed without any possibility of real-time human intervention. For the same reason Chang'e 4's landing had been 5 years earlier, the far side leaves no room for a joystick. Picture the ground it was aiming for. You are standing on the floor of Apollo crater, inside the older basin that contains it, under a black sky with no stars dimmed by any haze, because there is no air here to dim them. The gravity pulling you down is about 1/6 of what you are used to. A short hop carries you absurdly high and brings you back down slowly, almost gently, the dust kicked up by your boot, rising in a low arc and falling again in long, lazy seconds rather than the quick snap you would expect on Earth. There is no wind to carry that dust sideways. It simply rises, hangs for a moment, and settles exactly where gravity eventually pulls it, the same way it would have settled 4 billion years ago, the first time anything ever disturbed it. Nothing here erodes. Nothing here decays in any chemical sense. A footprint pressed into this regolith right now would, in principle, still be legible to whoever or whatever next set foot here in another 4 billion years, barring some catastrophic event in between, since nothing exists on this ground capable of erasing it on its own. The sampling system combined a drill capable of reaching 2 meters beneath the surface, with a robotic scoop for the surface material immediately around it, filling the sample container with a mixture from several different depths in a single operation. The total mass collected came to just under 2 kilograms, slightly more than the Chang'e 5 sample from the near side. 3 days later, the ascent vehicle lifted off from the top of the lander, the first launch from the lunar far side in history, climbed into orbit, and executed an autonomous rendezvous with the orbiter, transferring its sample container before being discarded. 3 weeks after that, the return capsule separated, entered Earth's atmosphere over the South Atlantic at more than 11 kilometers per second, and drifted down by parachute to the grasslands of Xizhiwangbanna in Inner Mongolia, where recovery teams were already waiting. When the capsule was opened, its interior was clean. The seal had held. Inside were the first rocks and soil ever brought back, physically, from the far side of the moon. The samples were moved to a laboratory at the National Astronomical Observatories in Beijing, opened under a nitrogen atmosphere to prevent contamination from Earth's own air and moisture, and catalogued within days. What they will eventually reveal is still, largely, an open question, and the most careful analysis will take years rather than months. The work itself, once it properly begins, looks nothing like the dramatic unveiling a documentary might suggest. A single grain of returned material, often smaller than a grain of sand, gets mounted in resin, polished flat, and examined under an electron microprobe, an instrument that fires a tightly focused beam of electrons at the sample and reads the X-rays the impact knocks loose, each element emitting its own characteristic signature in the process. That tells researchers more or less what the grain is made of. A separate technique, mass spectrometry, vaporizes a tiny portion of the same material and sorts the resulting atoms by mass, which is how isotopic ratios precise enough to function as a radiometric clock actually get measured. None of this requires large machines or dramatic instrumentation by the standards of a physics laboratory. It requires patience, exceptionally clean working conditions, and a willingness to spend months extracting a usable answer from a sample you could lose entirely in the crease of a glove. But the potential is considerable. If the drill core happened to capture fragments of the same mantle material the spectrometer had already detected on the surface nearby, the Chang'e 6 samples would offer something no orbital mission or remote sensing instrument ever could: direct laboratory measurement of mineral composition, trace element chemistry, and isotopic ratios precise enough to constrain both the age of the basin-forming impact and the thermal history of the Moon's interior. It helps to know what the sibling mission already achieved on the near side, because it shows exactly how much a single well-chosen sample can move an entire field. Before Chang'e 5, every lunar basalt anyone had ever dated, whether from Apollo, from the earlier Soviet lunar missions, or from meteorites, came out somewhere around 2.8 to 2.9 billion years old, and the consensus had settled around the idea that the Moon's volcanic interior had essentially gone cold and stayed cold ever since. Chang'e 5's basalt samples, precisely dated using the decay of lead isotopes, came back at 2 billion years old, almost exactly 800 million years younger than anything previously measured, and proof that the Moon's interior had stayed warm enough to erupt lava long after every existing model said it should have finished cooling. If Chang'e 6 can return a comparably precise date from the opposite end of lunar history, not the youngest eruption, but the very oldest, most violent event the Moon ever experienced, the two missions together would bracket nearly the Moon's entire geological life, from its most catastrophic moment to one of its last gasps of internal heat, using nothing but 2 small handfuls of rock collected 5 years and 1 entire hemisphere apart. That age matters more than almost any other number in lunar science right now. If the samples contain impact melt from the basin-forming event itself, rock that was liquefied by the impact and then solidified, it can be dated using the decay of uranium into lead, a clock that started running the moment the rock crystallized. A confirmed date would anchor the entire lunar cratering chronology, the method by which ages are assigned to surfaces across the solar system, calibrated against a small number of radiometrically dated samples, and then extrapolated everywhere else through crater counting. The method itself is simple enough to describe in a single breath, even though applying it carefully takes years of careful work. A surface accumulates craters at a roughly steady rate over time, the way a field left untouched accumulates footprints. Count the craters of a given size within a fixed area, and you get a rough sense of how long that surface has been sitting exposed, undisturbed, collecting impacts. On its own, that only gives you a relative age. This surface is older than that one, because it has more craters on it. To turn a relative age into an actual number of years, you need at least one place where you know both the crater density and the true age, measured independently, usually through radiometric dating of an actual rock sample collected from that exact surface. The handful of Apollo and lunar landing sites provided those anchor points decades ago. Once you have enough of them, you can build a curve relating crater density to age, and then apply that curve to any other surface in the solar system you can photograph closely enough to count craters on a crater-pocked plain on Mars, a heavily scarred moon of Saturn, a basin on Mercury you will never be able to visit directly. The method has its own complications, which careful researchers have to account for rather than ignore. A single large impact does not just leave one crater. It throws debris outward at speed, and a portion of that debris falls back to the surface nearby, forming clusters of smaller secondary craters that have nothing to do with independent impacts arriving over time, even though a careless count might mistake them for exactly that. Distinguishing genuine, independently arriving primary craters from secondary debris thrown out by one larger nearby event is a skill in itself, and getting it wrong in either direction can shift an estimated age substantially. This is one more reason a confirmed radiometric date from this basin's own material would matter so much. It would not just extend the calibration curve further back in time, it would let researchers check their secondary crater corrections against a genuinely independent measurement in a part of the Moon with an entirely different cratering history from every site used to build the curve so far. The entire chronological skeleton of planetary science, the dates attached to nearly every surface feature beyond Earth that has ever been described in a documentary or a textbook, ultimately traces back to that small number of Apollo-era rock samples every one of them collected from the near side of our own moon. It is a remarkably thin foundation for something so widely relied upon, and every additional dated sample from anywhere else, including, potentially, the center of the basin we have spent tonight with, makes that foundation measurably less thin. The existing calibration points reach back to about 3.9 billion years. This basin is older than that, and until a sample of its actual impact melt is dated directly, its age remains an estimate built on extrapolation rather than measurement. An uncertainty of even 100 million years at this end of the timeline propagates outward into our estimates for when comparable features on Mars, Mercury, and the moons of the outer planets formed. The samples may also help settle the late heavy bombardment question directly. The evidence for a discrete spike in impacts around 3.9 billion years ago comes mostly from clustering in the ages of Apollo-era samples, but those samples were all collected from a small number of basins on the near side, and skeptics have long argued that the apparent clustering might simply reflect the ages of those specific basins, rather than any genuine global spike. If you only ever sample 3 or 4 locations, their ages will cluster, almost by definition, because there are only 3 or 4 ages to measure. Far-side material, collected from a basin population that has never contributed to the existing dataset at all, provides a genuinely independent test. If it clusters around the same period, the bombardment hypothesis gains real support. If it spreads more broadly, the hypothesis weakens considerably. Either result would be useful, which is rarer in this field than it sounds. The Wolf Amendment shapes who gets to do that work. China set aside a portion of the lander and orbiter's payload capacity, specifically for international cooperation, and selected 4 contributions from outside China after a competitive process. France provided an instrument called Dawn, designed to detect radon gas escaping from the lunar regolith and study how dust and volatiles move between the surface and the thin lunar exosphere. It operated for about 32 hours on the surface. Italy contributed a passive laser retroreflector, a simple mirror-like device that lets future orbiting spacecraft bounce a laser pulse off the lander and measure the round-trip time precisely enough to pin down its exact position, the same basic technique the Apollo astronauts left behind on the near side decades earlier. Sweden, with support from the European Space Agency, provided an instrument called NILS, which spent nearly 4 hours measuring negative ions kicked up from the lunar surface by the constant impact of the solar wind. A small Pakistani-built CubeSat separated from the spacecraft to take its own images of the Moon and Earth before the landing. All of it, together with the lander's own modest mini rover, a roughly 5-kilogram machine nicknamed the Golden Toad for its gold-colored insulating skin, flew on a single mission whose primary purpose was always the 2 kilograms of rock and soil at the center of tonight's story. So scientists from those participating countries, along with researchers from other nations with active cooperation agreements, will have direct access to the return samples themselves. Researchers in the United States, absent specific congressional approval, will not. The samples are a scientific resource, but they are also unmistakably a diplomatic one, access to a piece of the solar system that genuinely no one else currently has. The first papers from this analysis are expected across 2025 and 2026. The work will be slow by necessity. The samples are irreplaceable, and every milligram used has to balance immediate scientific return against preserving enough material for future studies, using techniques that do not exist yet. The original Apollo samples, collected more than 50 years ago, are still being analyzed today with instruments their original collectors could not have imagined. The Chang'e 6 samples will likely be studied for decades after the scientists who first opened that nitrogen-filled container have retired. A few hundred grams of basalt and regolith are now sitting in a laboratory in Beijing, but the far side as a whole remains, for the most part, exactly what it has always been, a vast, mostly unread archive. The list of what we still do not know about it is considerably longer than the list of what we have learned, and it is worth taking that list seriously rather than rushing past it. We do not know, with any real precision, how much of Earth's water arrived through impacts during this same violent period rather than through some other route entirely. The late Veneer idea water and carbon-rich material delivered by comets and water-bearing asteroids during the same bombardment that was, at other moments, Sterilizing the surface outright remains one of the more actively contested questions in the field. Different isotopic studies of meteorites, comets, and Earth's own mantle point toward different answers, some suggesting most of our water arrived this way, others suggesting Earth held onto more of its original, primordial water than the simplest version of the story assumes. A basin this size, this old, this thoroughly mixed with material thrown up from deep inside the moon, may eventually help settle a piece of that argument too, once enough of its material has actually been analyzed rather than simply observed from orbit. We do not know the precise age of the basin. The best current estimates place it between 4.2 and 4.3 billion years ago, but an uncertainty of 100 million years sounds small until you notice what it spans the difference between a moon battered, while the Earth itself was still actively accreting material, and a moon battered after the Earth had already cooled enough to hold a solid crust and standing liquid water. The Chang'e 6 samples may contain genuine impact melt from the basin-forming event, and if they do, radioisotope dating will finally give us a number rather than an estimate. But those particular samples came from Apollo crater, a separate, later impact sitting inside the basin rather than from the original melt sheet itself. The ideal sample would come from somewhere near the basin's true center, where any surviving impact melt is likely thickest and least disturbed by everything that has happened on top of it since. No mission has yet reached that location. We do not know the bulk composition of the lunar mantle, even now. The spectrometer on Yutu-Two detected olivine and low-calcium pyroxene at exactly one location, a single small crater on a basin floor roughly the size of a continent. The mantle is not uniform throughout. It varies in mineral proportions, in trace element chemistry, in the presence or absence of minor phases like garnet or chromite, depending on depth and location. One spectrum, however unambiguous, cannot capture all of that variation on its own. The Chang'e 6 samples will help, but they too represent only one location. A genuinely representative picture of the lunar mantle will require samples from several sites scattered across the basin, ideally including its very center, where the deepest material was thrown up. We do not know the thickness of the lunar crust on the far side with any real precision either. The best current estimates come from gravity measurements taken by orbiting spacecraft, most notably the Gravity Recovery and Interior Laboratory mission, which mapped variations in the moon's gravity field using twin spacecraft named Ebb and Flow by a group of elementary school students who won a public naming contest, flying in close tandem and constantly measuring the tiny changes in distance between them as one or the other passed over slightly denser or lighter patches of ground below. The mission produced the most detailed gravity map of any body in the solar system to that point, including the Earth, and finished in December of 2012. In the most literal way possible, both spacecraft, their fuel nearly spent, were deliberately flown into the side of an unnamed lunar mountain, 30 seconds apart, in a controlled impact named afterward for Sally Ride, the first American woman in space, who had been closely involved with the mission's outreach work and died of cancer while it was still in progress. But gravity models, however precisely measured, require assumptions about density that cannot be independently checked from orbit, and those assumptions introduce uncertainty of their own. Direct seismic measurement would resolve the ambiguity outright. During the Apollo era, 4 seismometers were placed on the near side, operating from 1969 until 1977 under a program led by the geophysicist Gary Latham, and recording thousands of moonquakes and meteorite impacts over those 8 years. That network told us, for the first time, that the moon genuinely has a layered structure, a crust, a mantle, and a small core, much like the Earth's, only colder and quieter. But all 4 of those instruments sat on the near side. The far side has never had a single working seismic station of its own. Its deep interior crust thickness, mantle layering, the size and physical state of its core is still inferred by extrapolation from the near side, not measured directly by seismic waves passing through it. That may finally begin to change. A NASA payload called the Farside Seismic Suite, carrying 2 highly sensitive seismometers originally developed for the InSight mission to Mars, is planned to land within Schrödinger Basin, itself sitting inside the southern rim of the larger basin we have spent tonight discussing. Schrödinger is, on its own terms, a remarkable piece of ground, a peak ring basin about 320 kilometers across, young enough by lunar standards that its central mountains and surrounding fractures are still sharply defined, and unusual enough to host its own small patch of volcanic deposits, evidence of localized eruptions long after most of the moon's volcanism had already gone quiet elsewhere. Landing two of the most sensitive seismometers ever built for spaceflight inside a feature like that, sitting on top of the much larger and far older basin underneath it, is about as close as anyone has come to designing a single mission that could listen directly to two different chapters of lunar history at once. If the mission proceeds as planned, it will return the first seismic data ever recorded from the lunar far side, the first chance, in other words, to actually listen to what is happening underneath all of this, rather than infer it from gravity alone. There is a stranger, less settled mystery sitting alongside all of this, one that has nothing to do with craters at all. Across large parts of the lunar surface, orbiting spacecraft have detected patches of crust that are magnetized far more strongly than they have any obvious right to be, and some of the strongest of these anomalies sit close to the rim of the basin we have been following. Tonight, roughly on the opposite side of the moon, from other very large impact basins. Where this magnetism comes from is genuinely contested. One explanation holds that the early moon once had a working magnetic dynamo of its own, generated deep in a churning liquid core, the same basic mechanism that gives Earth its magnetic field today, and that surviving rock simply still carries the imprint of that ancient field. A competing explanation holds that the magnetism has nothing to do with any internal dynamo at all, that a sufficiently violent impact can briefly vaporize enough rock to create an expanding cloud of charged plasma, and that this cloud, as it converges on the far side of the moon opposite the impact site, can compress and intensify whatever magnetic field happens to be passing through at that moment, strongly magnetizing the crust there in the process. A third possibility is that some of the magnetized material is not even native lunar rock at all, but iron-rich debris from the impactor itself, scattered across the crust and carrying its own magnetic signature from the moment it cooled. None of these explanations has been ruled out. All three remain active subjects of published disagreement among specialists, which is a more interesting place for a question to sit than a settled answer would be. The dynamo explanation, where it does apply, raises its own separate puzzle. A small, rocky body like the moon should have lost the heat needed to keep its core stirring and generating a field within a few 100 million years of forming by most straightforward thermal models. Yet magnetized samples brought back by the Apollo missions suggest a working dynamo persisted for a surprisingly long time afterward, with some studies pointing to a weaker but still active field continuing for 1 billion years or more beyond the point where it was supposed to have already switched off. Exactly what kept the dynamo alive that long, whether it was the same kind of slow mantle overturn invoked to explain the unexpectedly young volcanism in the Chang'e 5 samples, or some other mechanism, entirely remains an open argument in its own right, sitting one layer beneath the still unresolved question of where this basin's own magnetic anomalies actually came from. The question of whether the bombardment really did spike sharply around 3.9 billion years ago, rather than simply declining at a steady rate, remains open as well, for the same reason we have already discussed nearly every sample old enough to test. The idea comes from a small handful of nearside basins, places like Imbrium, Serenitatis, and Nectaris, each one a few hundred to roughly 1,000 kilometers across, each one already filled with the dark basalt plains that give the familiar nearside its mottled appearance from Earth. The Chang'e 6 material, and whatever comes after it, is the first real chance to test that clustering against an entirely independent dataset from a part of the moon that has never contributed a single dated sample before now. There is a final, wider question worth raising before we leave this list, one that reaches beyond the Earth-Moon system entirely. Every rocky planet we have any hope of studying around other stars almost certainly went through something broadly similar to what we have spent tonight describing: a violent, prolonged period of late-stage bombardment, followed by a decline to something calmer, with habitability, if it arrives at all, only really beginning on the far side of that decline. We cannot yet observe impact basins on planets light years away. What we can do is use this moon, sitting right next to us, and preserving its bombardment history in unusually legible detail, to calibrate the basic physics of how that kind of bombardment behaves, how quickly it typically tapers off, how much water and organic material it plausibly delivers along the way, how large an impact a given size of rocky planet is statistically likely to absorb during its own early history. Every estimate astronomers currently make about how common genuinely habitable rocky worlds might be, anywhere in the galaxy, rests in part on bombardment models built using exactly the kind of evidence this basin provides. A scarred piece of ground, roughly the width of a continent, sitting on the far side of our own moon, is quietly doing double duty as a calibration point for questions about worlds we may never visit, orbiting stars whose light left them long before any of tonight's spacecraft were built. And the far side's radio silence, despite everything we have said about it tonight, remains almost entirely unused for its primary scientific purpose. The technology demonstration on Chang'e proved the basic concept works. No full-scale array has yet been built. The signal from the universe's dark ages, the 21-centimetre line, redshifted down into a band no telescope on Earth can cleanly hear, remains, as of tonight, still undetected by any instrument, anywhere, on any world. It has been waiting in that silence for over 13 billion years. It can presumably wait a little longer, but it will not detect itself. One more thing is worth knowing before we come back down to the surface of the moon for the rest of tonight's story. This basin, as large as it is not entirely alone. Mars carries a comparable scar of its own. Hellas Planitia, in the planet's southern hemisphere, is about 2,300 kilometers across and roughly 7 kilometers deep at its floor, slightly wider than the lunar basin we have spent tonight with, and noticeably deeper, formed by an impactor thought to have been somewhere around 370 kilometers across, even larger than the one that struck the moon. Mercury carries a smaller version, the Chang'e Basin, about 1,500 kilometers across, formed by an object at least 100 kilometers wide. All three basins date from roughly the same violent era in solar system history, give or take a few 100 million years, and all three sit on worlds with no plate tectonics to erase them. The inner solar system, it turns out, did not single out the moon for this kind of treatment. Every rocky body without weather or moving crust to heal itself still carries the scars from the same general period of bombardment, sized roughly in proportion to how large a target each world presented and how much of the original debris field it happened to sweep up. Hellas and Chang'e, despite being larger and in some ways more dramatic, remain far harder to study directly than the basin on our own moon. Mars has just enough atmosphere to drive dust storms and seasonal frost that slowly obscure and rework its surface. Never enough to erase a basin this size, but enough to complicate the fine detail. Mercury sits close enough to the Sun that any future lander would face daytime surface temperatures hot enough to melt lead, and a round trip for a sample return mission would be a far harder engineering problem than anything attempted at the Moon to date. The Moon's basin, 3 days airless, geologically inert, and now finally visited in person, remains the one example of this kind of scar that we can actually walk up to, drill into, and bring pieces of home. The Moon's basin is not a freak event. It is one example, unusually well preserved, conveniently close, and now, for the first time, partly sampled, of something that appears to have happened to nearly every solid surface in the young solar system that was large enough to be worth hitting. Set against that backdrop, it is worth asking what an actual human presence near this basin would realistically look like, rather than treating it as a distant abstraction. The current Artemis architecture calls for a crewed landing near the South Pole, inside or close to the basin's southern reaches, using a lander descending from lunar orbit after astronauts transfer from an Orion capsule. Early missions are planned as short surface stays, on the order of a week, focused on testing equipment and collecting samples by hand from terrain that, until very recently, no spacecraft of any kind had ever touched. Longer-term plans call for a small surface habitat and a pressurized rover capable of multi-day traverses away from the immediate landing site, drawing on solar power gathered from the same near-permanently sunlit ridges that make places like Shackleton's Rim so valuable, and eventually on water extracted from the permanently shadowed ground nearby. None of this exists yet in any completed, flight-ready form. Every piece of it depends on engineering that is still being tested. funding that is still being argued over year by year, and a political relationship between the United States and China that shapes, in ways both countries acknowledge openly, how quickly any of it can actually happen. China's own roadmap, organized around its International Lunar Research Station, follows a broadly similar shape on a different schedule: robotic survey missions first, then short crewed visits, then, eventually, something meant to operate continuously rather than in short bursts. Both programs are aimed, more or less, at the same patch of ground. Whether they end up cooperating, competing, or simply operating in parallel without much reference to each other is one of the more consequential open questions in this entire story, and it is being decided now, in budget meetings and diplomatic cables, rather than in any laboratory. The lunar night has fallen on von Karman crater. It falls every 14 Earth days, and it has been falling for 4 billion years. Yutu-Two is motionless now, its solar panels folded, its electronics kept just warm enough by the slow, steady decay of plutonium inside its radioisotope heater unit. Outside, the temperature has dropped past -190 degrees Celsius. The basalt plain is dark, lit only by starlight, and the faint glow of sunlight scattered off dust drifting in the plane of the solar system. There is no wind to stir the regolith. There is no sound at all. The rover has now logged more than 70 lunar days of activity and driven a little over 1.5 kilometers across the floor of the basin, a machine designed for 3 months. Doing this for years, in a place where nothing has ever made this much noise on purpose before. Somewhere behind it, on the plain it has already crossed, sits a small crater with no name, too minor to appear on most maps, where a spectrometer once read 2 absorption bands and resolved a question that had been open since before some of the people reading the result were born. Somewhere nearby, sealed inside a canister that has long since gone cold and still, is what is left of a single cotton seed that managed, for about 9 days in January of 2019, to be the first living thing to grow on the surface of another world before the lunar night reached it too. That rock in the small crater was formed perhaps 100 kilometers down, inside the slow-churning mantle of the moon, long before there was a moon goddess to name a rover after, or a language in which to name one. It sat there for hundreds of millions of years while the young solar system finished its worst violence. Then, between 4.2 and 4.3 billion years ago, an object at least 200 kilometers across struck this part of the moon at a speed of perhaps 20 kilometers per second, excavating a hole 13 kilometers deep and 2,500 kilometers wide, and throwing that one piece of mantle rock outward into a blanket of ejecta on the surface. Lava covered it. Smaller impacts ground the layers above it into dust. It sat in the dark, buried, for almost the entire history of the moon. Then, a few million years ago, or perhaps a few tens of millions, something small struck the ground nearby, opened a crater 72 meters across, and finally exposed it again to sunlight, where it sat for the rest of that span, slowly darkening under solar wind and micrometeorite weathering, until a 6-wheeled machine the size of a desk drove up to the rim and pointed an instrument at it. That is the fact this whole night has been circling. A basin large enough to be mistaken for a feature of the world, rather than a wound in it. A piece of the moon's interior that had to wait 4 billion years, and travel no distance at all to finally be read. A silence on the far side deep enough to have kept both of those things intact, untouched, legible, for longer than almost anything else in the inner solar system has managed to stay legible at all. The basin does not know it was found. The silence does not know it is being listened for. None of this was waiting for us in any sense that requires intention. It simply sat there, doing nothing, for 4 billion years, because nothing on the far side of the moon has ever had a reason to disturb it. We arrived anyway, slowly, across 6 decades of photographs and probes, and one patient rover that outlived every estimate of how long it should have lasted, and we are still only partway through reading what is there. Out past the basin's rim, Chang'e continues its slow loop around the second Earth-Moon Lagrange point, listening for a signal that will not come again until the sun rises over von Karman. The Earth sits invisible in the black sky above the far side, exactly as it always has, exactly as it always will. The rover's instruments are off, conserving what little power remains, waiting out the cold the same way it has waited out more than 70 nights before this one. It will wake again, The panels will warm in the returning light. The mast will lift. The cameras will take a panorama of a plane that has not changed since the rover last saw it, and the slow traverse will continue a little further across ground that has been waiting considerably longer than it has. 4 billion years is a long time to keep a secret. 70 lunar days is not very long at all, set against that, and yet it was enough. Good night.